All right. So, just pick up and do a quick review of what we had last time. So last time in class, we saw with in the lecture, we saw how we've got evidence now for why you were told in middle school the first energy level holds 2, the second energy level holds 8, and so forth and so forth. So we've got data, first ionization energy data that we looked at, and we saw that between helium and lithium, there was a big jump or big drop in ionization energy, which means that we went from one shell with 2 electrons to a third or a second shell for the extra electron in lithium. We saw the same thing with neon to sodium. So we got neon, 10 electrons, 2 electrons in the first energy level, 8 electrons in the second energy level. For sodium, we got 2 paths. We could put the 9th electron in the second shell, or we could make a new shell. And if we look at the data, it says new shell. Because for us to get a drop in ionization energy, we would have to have the electron further away. If it was a 9th electron in this same shell, we would see that the ionization energy from neon to sodium would actually go up. Because we're assuming that the distance the distance between the electrons in the valence shell and the nucleus of neon would be about the same if we had just 2 energy levels for sodium. We'd expect probably a little bit of difference, but not something that's going to make this big of a difference. So the only way for this to happen is if we have the electron adding another shell. Questions about that? Now, I've got this equation up here because, as we've said from day one of starting these lectures, this equation is telling us how everything interacts. It's telling us about the attractions that are going to take place. It's telling us about the repulsions that can take place. Our focus is going to primarily be on the attractions, but we also have repulsions to take into consideration when we're looking at some of the trends that we're going to look at. Okay? Does anybody have any questions before we go jump into the next part?
But actually, I'm done with the book.
So, where are you going?
Doctor.
Okay.
So we'll talk tomorrow.
All right.
I finished it Saturday night.
All right.
Okay. Bye.
Oh. Okay. Bye. No cavities, right?
Orthodontist.
Getting them tightened?
Maybe.
Maybe. Okay. So, this basically is just definitions. I just used the term valence electrons. I think last time in class we talked about valence electrons. It's a term that you guys have already been introduced to. Okay? So valence electrons are going to be electrons in the outermost shell. If they are not a valence electron, they're what we're going to call a core electron. That's probably a new term for you. Okay? There's some patterns and trends that we can look at the periodic table to that help us if we know how many valence electrons there are. Questions about this? Yes.
So the number for the valence shell can be different based on what kind of atom it is? Like, if the atom has 4 shells, the 4th one is a valence shell?
Yes.
Okay.
Yes. So for hydrogen and helium, they only have the one energy level. So their valence shell would be the first energy level. Lithium all the way over through neon on the periodic table. The valence shell for that is going to be the second energy level. The 2 electrons that are in the first energy level, those are going to be your core electrons. And we just keep building up from there. So on the periodic table, as it stands right now on the periodic table, we only have our highest valence shell for any atom is going to be the 7th shell. Okay? Other questions? All right. Now, the core electrons are important because unlike, we haven't paid much attention to it. We've mentioned it. But the core electrons are going to drastically affect what the attraction between the valence electron and the nucleus is going to be. Now, one of the things, and it goes on to the next slide as well. I don't know how much time I'm going to spend on it, but we can calculate a value that we call core charge or effective nuclear charge. And the core charge or effective nuclear charge, and I've got it italicized, it's an approximation for the attraction or what effect the core electrons would have on the attraction for that valence electron. So these 2 atoms here represent the same atom. They represent sodium. So this one represents sodium, and it's got 11 protons. Everybody look at it on the periodic table. So it's got 11 protons. It's going to have 3 energy levels, or 3 shells. And we know the first shell has 2 electrons. The second shell has 8 electrons. And that 11th electron is going into 3rd energy level, so there's 1 valence electron. When we think about the core electrons and the effect on the valence electron, we are only going to think of it as an outward repulsion. We are not going to concern ourselves. I'm not saying it's not a factor, but we're not going to concern ourselves with the interaction between these particles, the electrons that are in the core. All that we care about is what is their net effect on that valence electron. And for us, that net effect is always going to be a reduction in the attraction because it's being repelled outwards. Now, the reason why I changed this number to a 1 is because we can essentially say that approximately, again, I emphasize this approximation, approximately the repulsion outwards from the core electrons on this valence electron is canceling, quote unquote, because that's not how it actually works, the attraction of 10 of those 11 electrons. Again, this is an approximation. If we actually went through and did all the really involved calculations for what the effect of those electrons would be on this valence electron, it may not end up being a net effect of 1. It's probably going to be a little bit more. So the repulsion of those core electrons is going to reduce the attraction on the valence electron. This equation describes what the approximation would be. So Z effective is going to equal the number of protons minus the number of core electrons that you have in the atom. So for potassium, is this big enough for you people all the way in the back? Okay. So my effective nuclear charge is good for potassium would equal 11, because that's the number of protons, minus the number of core electrons. Now the number of core electrons is not the easiest thing just to look at the periodic table and tell. Okay? So I'm going to give you a way of doing this that's relatively quick and easy. Does anybody know how to look at a periodic table and tell how many valence electrons it has? Cameron?
It's just like each row, right?
Row or row?
Oh, up and down.
That's column.
Oh, column then.
So explain that a little bit more.
So like the first one has 1, the second one would have 2, and then the third one would have 3, and then, but it's like all the transition metals, all of the same, right? So like the entire like middle part would just count as 1.
So you're okay. So if you look at the periodic table, people, what Cameron's talking about are the tall columns. We don't include the short columns in there. Okay.
So you just skip them. Okay. Well, then you just count them left to right. One has 1. The second one has 2. The third one has 3.
Now, I've got the Roman numerals up here on the board. 1 through, for most of them, 1 through 10. For those of you who are not familiar with them. Now, look at that periodic table that I've got taped to your tables. Think about what Cameron just said. And what can you look at to determine the number of valence electrons? What, Lincoln? You mumbled something.
Yeah, I did. I just said the Roman numeral tells you
Roman numeral touch. And what don't have Roman numerals?
transition.
Transition metals. So is that a term you guys are familiar with?
Yeah.
Transition metals? Okay.
I don't know.
All right. Now, so if you're not familiar with that term, that's the area of the table from scandium over to zinc, so number 21 through 30, up and down as well. Okay? So the short part of the periodic table. Now, one of the problems is that I'm old. So I use some old stuff on the periodic tables. Roman numerals are not used on most periodic tables now. Can you find a pattern if you're given the 1 through 18 numbering system that you could use to determine the number of valence electrons? Logan?
Well, the first two are just 1 and 2, and then you just take the second number of the 1 through 18.
So if you look at so group 1 and 2 are still 1 and 2, but then we pick up with the tall groups at 13. Look at the ones place, and that'll tell you how many valence electrons. Everybody okay with that? So if you're not given a periodic table with the Roman numerals, that's the easiest way to do it. The 1 through 18 numbering system is now the standard that's used. Okay? Now, that tells you how many valence electrons. Well, how do you determine the number of core electrons then? Well, you got a total number, right? And if you know the valence, all other electrons are what? They're core electrons. So if I've got 11 electrons and one of them is a valence, then how many core do I have? 10. Now, we call that a positive 1. And I'm going to learn from my period 6 class, it's a positive 1, but it's not representing a repulsion. Because we've been saying repulsion's a positive value, right? What this is representing is the charge, the effective charge of the nucleus. Andrew?
Would that be potassium or sodium?
Oh, sodium. Because that's for,
Sodium's 11, so potassium's 19.
so I need to go to 19
Yeah.
minus 18.
Yeah.
Sorry. I was doing sodium, yes. We get the same thing though, right? The effective nuclear charge for our potassium is A plus 1. So this is the charge of the nucleus that the valence electron is affected by. Yes, potassium has 19 protons. It's got 19 electrons. One of those is a valence electron. 18 of those are core electrons. So that one valence electron is being repelled by 18 electrons. That repulsion is reducing the attraction of the nucleus, making it look like the valence electron is only attracted by a plus 1. Okay? That's what effective nuclear charge is. It's taking into consideration and looking at, yes, there's attractions, but we also have repulsions from the electrons. And those repulsions reduce the attraction for the nucleus. How much? Based on that equation, a 1-to-1. So for every core electron, it's canceling, again, air quotes, because it's not, right? That's just what the equation is saying. It's an approximation. Okay? The last bullet's probably the most important. As your core charge increases, the attraction of valence electrons increases. Well, that's almost a duh statement, right? Anymore. Because if I were to make this value, so Q1's always going to be an electron, right? It's -1. If this value here is going up, what has to happen to the magnitude of V?
It goes up.
It's got to go up. Okay. I'm going to give you an element. I'm going to try. I am blanking with this class in terms of names. Yeah, go ahead and hold them up so I can see them.
Tape it to your forehead.
All right, put them down. I'm going to try. I'll give myself like a 5 count. If I can't get on 5, then I'm going to ask you to give me the flashcard. Grace, you're going to be lithium. Kylie. No, I got it right. You're going to be beryllium. We're not Kenzie. Kenzie's in green. All right. All right, I can't remember. Show me your card. Yeah, show me your card. What? I can't hear you.
He asked for the card.
Card. Lily. Boron.
It was back at the table. You just said, I was really confused on what it was until you started telling them to do that.
That's from my AP class. Cameron, you're carbon.
Yes.
Luke, you're nitrogen.
Boom, it's 2.
I give up. Maggie. Did I give Luke your nitrogen?
Yeah.
Oxygen. Rylan, your fluorine. Casey, your neon.
You just figure out the effective energy.
Not
You're not
Nasser?
on the valence electrons.
Okay. Your sodium.
Effective
I give up.
It literally says there.
Abby, your magnesium. Logan, your aluminum. Katie, silicon. Shelby? No. Skylar, your phosphorus. Lincoln, sulfur. Kenzie, chlorine. Andrew, argon. Irons. I can't remember. What is it?
My name's Jonah.
Jonah. I almost called you Luke, so I just switched to the last name so I wouldn't, yeah. Potassium. Bread. Calcium. Allison. Gallium. Aiden. Germanium.
Mine or yours?
Emma.
Plus,
Ella. I was one off in the alphabet. Ella, arsenic.
I want to be arsenic.
I give it. Lauren. Selenium. I know the last name. I don't call you by your sister's name. What's your first name? Lauren? Mara. Did I give bromine out yet?
No.
Bromine. And then Maya, your krypton. Calculate the effective nuclear charge, and you're going to do this as the activity. So a near pod. Make sure you do the things I asked for there. I want you to identify how many protons, how many electrons, what's core, what's valence, so on and so forth. So some of the stuff I asked for is not required to do the calculation for the effective nuclear charge. But I would like for you to give it to me. curious, once you guys submit it, can you go back to edit it?
Yeah.
You can?
You just
Okay.
press a button that says.
Unless you like close it.
Okay, but until I close it, you guys can go back and do it?
Yeah.
All right.
What flavor do you Oh, my question just got that one off there. No, thank you. No, that's valence. That's the production energy. Yeah. Or, I wrote an organ. Wait. You messed up a symbol subtraction.
Okay.
Yeah. Then he should have gotten negative number.
Try to finish these up here next 15 seconds or so.
So you do 7 minus 5. No, there's 5 valence electrons. Oh, you subtract valence before.
If you've got the drawing done but you haven't hit the submit, go ahead and hit the submit, please.
Wait. No. So we subtract to get the whole
Steal it.
Okay. Who had lithium, sodium, and potassium? Raise your hands. Grace, what was the number of valence electrons? Lincoln, what'd you have?
I had some.
Oh, you had sulfur. Jonah,
I had potassium,
and what was its number?
plus 1.
So this is the formal charges. Who had beryllium, magnesium, and calcium? Brett, which ones you have?
Calcium,
What was your number?
+2.
Who had magnesium? What'd you get? Who had boron, aluminum, gallium? Logan, which ones you have? Aluminum?
Yeah,
How much?
+3.
And Allison, what'd you have? And what'd you have? All right, everybody see the trend here?
It's bigger.
What's it the same trend as?
Valence.
What's that? Valence electrons. Remember I said the valence electrons, we look at the top part and we say, you know, the number tells us what the valence electrons are, except for the middle elements, the transitions. The same is true for our core charge or our effective nuclear charge. If you think about it, it makes sense. It's the valence electrons, or it's the core electrons that are being subtracted. Right? So, if it's the core electrons, subtracted from the number of protons, that should equal the number of valence electrons. If it is neutral. Okay? If it is neutral, that's going to be the case. If you have an ion, remember, an ion is something that's gained or lost electrons, then these can change. Your core charge or effective nuclear charge may change if you have an ion. We'll see those near the end of class today. Okay? All of these in the middle, plus 2s.
Wow.
Now the reason why they stay at plus 2 is because for those elements, when you add the electron's not a valence electron. It's going into the core. That's something we'll learn more about later this week. Okay? I don't know why my positive sign on the 8 didn't show up. Questions? So, in general, what is happening to the attraction for the valence electrons as you go from left to right across the periodic table? It's going to get higher. Has to. Again, if we look at this equation, you're increasing this value for Q. Okay? All right. So we switch gears slightly. What we're going to start doing now is we're going to start looking at what we call periodic trends. There are certain properties about the elements that are important for how they act chemically that we can look at the periodic table and make some predictions about. Now, my goal is for you guys to be able to explain the reasons why. Now, there are many reasons why. There's plenty of reasons way above first year chemistry at the high school level. So our focus is going to be on attractions and repulsions and the think factors that affect those. As of right now, you have all of the explanations for the most part to be able to describe why is it these things take place. Why is it that something increases or decreases? Okay? That's what we've built over the last couple of lectures, is the reasons for why the things are going to happen the way they are. Okay, so you are definitely going to have to look at your iPad for this. Either look at, I've got it up on both the Notability as well as Nearpod. Yeah, you can look at Notability or you can look at Nearpod. If we go to answer the questions that I'm asking over there, let's start off with the first. What is the trend in atomic radius, or what trend in atomic radius is observed as one moves down a group? So up and down on a periodic table is called a group. It's also called a family, not as frequently. We're going to call them a group. So as you go down a group, what's the trend in atomic radius? Jonah? Goes up. Now, why? Cameron?
Is it because they get more shells?
That's it. It's not the only reason. It's the primary reason. We've seen that as you add more electrons, you get a certain point and then you add another shell. And each time you add a shell, those electrons are going to be further away from the nucleus. As you go down a group, all of them have the same number of valence electrons, the difference being what shell are they in. Lincoln?
Oh, I was gonna say, is it also like based on how stable they are?
No. And this is where I battle the really bad things that they have taught you in middle school that hinder your learning into high school and beyond. They've made a big deal out of the noble gases, haven't they? You get 8 electrons, you get an octet, and all of a sudden you got this magical element. There's nothing magical about it. It's trends. The only thing that I would say is magical about a noble gas is that the next element that goes into an atom is going to go in the next shell. That's it. So when we talk about stability, we're going to be talking about the attractions and repulsions. Okay? So if you look at the periodic table here, and we see that these noble gases are the smallest within a period, there's a reason for that. And their size also has an effect on what their chemical properties are going to be. So, yeah, the noble gases are stable chemically, but it's because of the properties of the atom itself. And we can see these trends occurring as we go along, okay? Now, let's answer the third question and then look at another property here. So, is the core charge a significant factor in this trend? So if I'm going down a group, is the core charge a factor? Go to the previous slide. We're looking at the up and down.
No.
Jonah?
No, because all the groups have the same core charge. So
Now, one thing I do want you to keep in mind is that we say it's a +1 for all of the elements in this group, right? But is it +1 for all of them? No. Remember, it's an approximation. Okay? But what we can say is that they're all approximately going to be about the same or very similar. So the core charge is not going to be a factor here because it's not changing. If we look at the groupings themselves, we have the same core charge up and down, so that should not be a major factor. The major factor is the number of shells that you have. As you go down a group on the periodic table, you add a new shell. So francium, to group 7, period 7. So left to right on the periodic table is periods or series. I call them periods because that's how I learned it long time ago. So most textbooks will call it, but you also see it called a series. Just like up and down as a group or a family. group is the much more common term, but you will see the term family used. So francium is in the 7th period. That means it has how many shells? 7. It's going to have the largest size because in that group, because it's going to have the most shells within that group. Everybody okay with that? Oh. Now, why, if I told you that as you go down, the elements further down in a group, so if we're talking about group 1, talking about rubidium, cesium, francium, if I told you that those elements actually get bigger than what you would predict, what would be the reason why? Yes, they are getting bigger because you have more shells. But if I said that they're a little bit larger than what you would expect, what would be a reason why? Allison?
Is it because when ion distance decreases, ionization energy decreases?
They're related. But I'm just looking at why would they be bigger than what you would expect? Now, when I say bigger, I'm talking about the radius. And I guess I should have been clear about that. So everybody knows what radius is, right? Okay. So why for rubidium, cesium, francium, if we actually could measure it, why would they be a little bit bigger than what you would expect?
So maybe all the electrons, they might push each other out.
Yes, absolutely. Now let's look at what's going on here. Okay. So if we go down that group, hydrogen. So the elements, core electrons. How many core electrons does hydrogen have?
1.
None. It's only got 1 electron. It's in the outermost shell. There are no core electrons, right? So it has 0 core electrons. Lithium. So I'm just going to go down the group. Lithium. How many core electrons does lithium have? 2. Sodium.
Or no, 10. Yeah, 10. 12.
Everybody okay with 10?
Yes.
Skylar, you okay with 10? Okay. Well, I thought you were saying something different.
No, you looked at us with a disappointed manner. I thought we messed up.
Oh, no. That's just my
You said 10,
that's just my poker face.
Oh.
I don't want my face to give away whether you get the answer right or wrong. I always sow doubt in your answers because I want you to be confident about what your answer is. Even if it's wrong, I want you to be confident in it. Okay? 10. Potassium.
18.
Everybody okay with 18?
Yes.
Rubidium.
36.
There's your why, people. We get a pretty big jump there between rubidium or potassium and rubidium, right? When we get to cesium,
54.
Oh, no.
Yeah.
Yes, very much so.
You just subtract 1.
Never mind. I'm not even gonna explain myself.
okay. So, rubidium and cesium are bigger than what you would expect based on just adding another shell, because you have a pretty big jump in the number of electrons that they have. That's why. So, the primary reason going down a group that they get bigger is you add a shell. The repulsion of the electrons also contributes, especially to the elements further down. Lincoln?
This is kind of off topic, but not really.
I'm up for an off-topic question.
So for valence, or for like the shells, I feel like our teacher tried to explain to us that there can be, like there's normally this many, but there can be up to this many in a shell, and I never understood what she was saying.
Okay, so the first energy level can hold 2 electrons. The second energy level can hold 8. The third energy level can hold 18. The fourth energy level can hold 32.
That's it? Or I mean, like, is it like a set number, or is it like, or
That's the formula. N would be your energy level. So if you were to plug in, so if I were to plug in 1, so if N equals 1, then that's going to equal 2, because 1 squared is 1, times 2 is 2, right? Second energy level, oh sorry, that N is equal to 1. Electrons, 2 electrons. If N is equal to 2, 2 squared is 4, times 2 is 8.
okay.
N is equal to 3, 3 squared is 9, 3 squared is 9, times 2 is 18.
I don't know what my teacher was talking about. She said that
They don't know what the hell they're talking about. That's why they shouldn't be talking about this stuff in the first place.
She was like, yeah, you learn more about this in high school. For 2 years.
I'm sorry. I know there's one teacher who has a chemistry background because she worked at Lilly for years. That does a pretty decent job. But so if we got up to N is equal to 5 in the 5th energy level,
50.
it's 100 electrons, right? No, I'm sorry, 50 electrons, because 5 squared is 25, times 2 would be 50 electrons. There's a difference, though, between how many electrons can there be on an energy level versus how many there really are based on what we have on the periodic table. Remember ground state, right?
Yeah.
Ground state, the lowest energy state that the electrons want to be in, right? Well, there's a specific pattern. This is what we're building to, okay? So Friday probably, we're going to build up and have an understanding of why we have the number of electrons where they are, okay? When we get to the 5th, so to describe the elements on the periodic table, we need 7 energy levels. Of those, only 4 are filled. The others have more room. Okay? And I know that seems confusing and stuff, but we'll see why later. Okay? All right. What is the trend in atomic radius that's observed going from left to right across a period? So I think I mentioned it earlier. Left to right on a periodic table is called a period. It's also called a series. I'm going to call it a period. Luke, you got the answer already?
No.
No? Stop flirting then. Okay. I'm going to let people think for a second, Cameron. I'm going to let people think for a second. Although, Rylan, I'm going to call on you because Cameron's given the answer several times now. We'll spread the wealth a little bit. Okay? No, I heard you. All right, Rylan.
It goes down.
Oh, I thought I was asking what. Yeah, you're right. That's obvious. It goes down. Now, why? That's what I thought. That's what I was waiting for.
Answers.
Okay, so, because there's more, because as you go from left to right, the valence fills up with more of electrons. Like the number of valence electrons increases, so it goes down.
Okay, so everything you said is right.
Oh, okay.
Nothing that you said is wrong. But it doesn't necessarily tell me the why. You're right. As we go from left to right, except for these elements right here, we're going to be adding another electron to the valence shell. Okay? And they get smaller. We can see that from the numbers. But why? Allison?
Is it because as the charge increases, so does, or the attraction increases too?
You go back, we got our core charges going up, right? So, with a +1 core charge versus a +8, based on our equation, now keep in mind, the thing that we're not looking at that is changing, we know it's now changing because you see it on the graph, is at our distance. But if we look at just this top part, Q1 is always -1, right? Q2 is going to be positive, whatever our effective nuclear charge is. So if we're going from +1 up to 8, this value, the magnitude, remember, has to do what? If this goes up, it's got to go up. It's numerator. It's a direct relationship. So Allison, you're right. Our core charge is why they are getting smaller, because the attraction is getting greater. Lincoln?
This isn't scientific at all. I just but like, is it like getting smaller too because like whenever you have the +1, it like wants to bond or like do something with another atom, so it's kind of like distancing away from the nucleus so that it can't. Or is that not why? Okay, I was just wondering. I was curious.
When two atoms come together to start, and we're going to talk about chemical bonding second semester.
Okay.
When two atoms approach each other, we are going to see that there's attractions between the nucleus of one and the electrons of the other, and the size of the atom and the structure of the electrons changes during that process. We're not worried about that right now, but if we look at just the size of an atom, as we go from left to right across the periodic table, those added protons are going to increase that attraction, causing them to get smaller.
Okay.
Okay? Now, we are also adding electrons, right? What is adding electrons going to do? Andrew?
The electrons are going to still repel each other out of or outside of the atom, like just a little bit. No?
What wins? If you're absolutely right, you're going to get more repulsions because you have more electrons. You're going to have more repulsion. Which, if you got more repulsions, what would you expect to happen to the size?
Get bigger.
Get bigger. But what are we seeing? Get smaller. So what wins? The added proton or the added electron? Yeah, the proton. So the attraction from the protons is going to win out in this case over the repulsion that the electrons are going to encounter. Everybody okay? Okay. So I'm going to have you answer a question here. I'm going to keep this up on the screen for you guys, and before you start answering it, I'm going to set it up. I'm going to just say answer the question because I'm going to give it to you here. Before you start answering it, I want to make sure you understand what I want to know. Okay? So I don't have these to scale. But based on our information on periodic table, let's say this was the second or third period. There's only 8 electrons in those periods, right? Second or third row. So this with a core charge of 1 would be the largest. This would be the smallest. Okay? And we see that based on the numbers. Now, what I want to know is between which 2 radii. And I'm not talking, I'm going to take this one off the table. This is what, it's not between 1 and 8. We know that. What I want to know is between which neighboring ones, between which 2 atoms, would you get the greatest change? In which 2 would you have the least change in size, and why? I want to know why. Think about it, answer it. If you got any questions or you need clarification, ask. Kenzie, do I need to make it bigger for you?
No, I have a picture on here now.
Okay.
I'll just read it out.
All right. Make sure you pull up on Nearpod, because I've got the question live there. So between which two atoms, neighboring atoms, would you have the greatest change, and which two would you have the least change, and why? Once you've got it, make sure you submit it so I can take a look at the answers as they come in. Lincoln, you got a question, or are you going to
I
answer?
got a question.
Go ahead.
Right now,
Why not?
would the 8th one and the first one be considered neighboring?
No.
No.
Remember, I took that off the table specifically.
Huh?
This and this, no,
Okay.
because that's the most obvious. So between the neighboring ones, like between these two, these two, these two,
Okay.
does that make more sense now?
Yeah.
Okay. Luke, I need a reason.
For what?
Your statement?
Oh, I'm editing it right now.
Oh, okay. Because you guys, on these ones, you can also go back and read and edit?
Yeah.
Okay.
One to two, that's times two, 78, that's times one. No, that's an eight. It's plus a seven. Eight, nine. Three plus seven doesn't seven.
Is this something you can prove like mathematically, or is this just like common sense?
Mathematically.
Okay.
There's a very mathy reason why. There's also, you can also reason it out without math, but you'll see when we look at the math part, you'll see, oh yeah, that looks like a number. Okay. All right. I know. I'm gonna give you like another 45 seconds or so. You want to wait and see what the answer is?
I will. I was going to try to avoid being in close contact. That's really what I was doing. So I've been 14 minutes.
All right, submit what you got. Even if you're not done, we got to cut off time at a certain point.
I think I got it.
All right, let's get them in. Come on. I got 4 of you still. All right, as you see, this is
Oh, I said the opposite.
that's is it okay? I need to know the exact pronunciation so I do it correctly for the rest of the year. Nasser? Okay, so the up front is where the emphasis is. All right. So this is Nasser's. So you would have the greatest change between the first and second because you have double the amount of protons. And this would mean a greater attraction, which would be closer, would mean a closer radius by 2 times. Now I'm not worried about it's not necessarily 2 times with the radius, but you've spot on with, you've got double the number of protons from here to here. Which means if you look at this, you're going to double the attraction, right? It doesn't necessarily translate perfectly to the size, but you do have double the attraction, which means you're going to have the biggest change. It also, in the valence shell, we go from 1 valence electron to 2 valence electrons. Now what happens as we continue to add valence electrons is the repulsions now start to build up. Along with the fact that when we get to the 7th and 8th, we go from 7 protons to 8 protons, proportionally. And Lincoln, this is where that math part comes in. Proportionally, a change from 7 to 8 is not nearly as drastic as going from 1 to 2. Along with the fact that you have more electrons. So you've got the repulsions building up, and you've got they don't want to come in because of repulsions, and the change in attraction is not all that great. This is why it's less. And if you go back and look at the values, so if I look at sodium to magnesium, look at yours because you can't see these numbers. We go from 190 to 145. That's a change of 45. Versus at the end here, where from chlorine to argon, we get a change of 8. 45 versus 8. It's 5 times less, right? Now, we don't have a mathematical equation that we can plug in to give us that specific value, other than we can use this equation to help us look at the relationships. And then as we move from left to right, the change in positive charge for the nucleus proportionally is less, as well as the number of electrons being greater, meaning we have more repulsions. So it's going to be harder to pull them in. Questions? You good? Okay. All right. Now we haven't done much with ions. We're going to look at how ions change or don't change our trends here. Okay? I don't know why I originally put identify the valence shell when I've got right here the valence shell. So what we're going to do is I want you to identify how many electrons are in each of these ions first. I don't have that on a table here. So if I've got sulfur, how many electrons does neutral sulfur have, class? 16. What does the -2 charge mean for sulfur? Cameron?
Is it gaining 2 electrons?
Gains 2 electrons. So how many electrons is a sulfur with a 2 negative going to have?
18.
18 electrons. Okay, so what neutral element would have the same number of electrons, 18, as sulfur with a 2 negative?
Argon.
Okay, we'll get to this last one here in a bit. Is that our 5-minute warning or no?
Yeah.
Okay. So, next, chlorine. How many electrons is chlorine going to have as a -1 ion?
18. Argon.
Now, potassium.
19.
Potassium has 19, but
What
this
is-
time around it's a +1, meaning it's done what?
Losing, so it's 18, so it's argon again. Oh my god.
Whoa.
Argon.
What? Okay, so here's what I want you to do now. I want you to calculate the core charge. Now, keep in mind, this is a little bit different. I'm going to jump down to potassium. Potassium ion. Potassium's in the 4th row, right? Neutral, it would have what electron in what shell? The 4th shell, because it's the 4th row down, right? What have we done with that electron, though? We got rid of it. So is the 4th shell now our valence shell?
No.
It's the 3rd. So, when we go to do the effective nuclear charge, the number of protons in potassium has not changed. It's still 19 protons. But we only have 10 core electrons. Here's why. So I've got 19 in the 1st shell. How many electrons can you have?
2.
So you have 2 electrons. In the 2nd shell, you can have how many?
8.
Now, our 3rd shell, we can have more than 8, but right now, we have 8. But this is our valence. These are our core. And remember, our effective nuclear charge is the number of protons minus core. Okay? Here's what I want you guys to do for next time. Sorry, you do have just a tiny bit of assignment. Finish the calculations for core charge for sulfur, chlorine, and calcium. When you're walking in with that, we'll pick up with these when we get back on Wednesday. Okay?
What do you want us to do with the name tags?
Name tags.
Do you want them back?
Pass them up to Cameron. Cameron's going to collect them. Thank you, Mr. Short. want. I don't even. Is that all of them?